we're going to talk about packings and nets. So usually packings in the literature are called nets, but nets in geometry are overused, overloaded. So when I remember, I would try to use the word packing. Once in a while, I'm sure I would use the word nets. And okay, so we're again in a metric space setting. We have a metric space. Again, think about this just as the plane. And I have a subset of the metric space, so some set. For our purposes, usually it would be a set of points. And a subset N of P is an R packing if it has two properties. Okay? The first property is a covering property. Covering. Namely, all the points of P for all P in P, we have that there exists a point R in the net. Well, R is not a good choice. V in the net, such that the distance between P and V is at most is smaller than R. Okay? Okay, so this is very similar to the property we seen for K-center clustering, that you're covering, the centers cover the points that we radius to R. And the second interesting property is separation, which means that we need to spell it correctly. Separation property, which implies the following: for any 2 points X and Y in the net, their distance XY is at least R. Okay? And it's kind of, it's a minor technicality, but it's kind of important that here it's smaller, strictly smaller, and here it's smaller and larger equal. Okay? So, and we already seen a net, essentially, when we talked about the doubling constant. So, how to compute a net, a packing, an R packing. Well, you do the obvious thing, right? You start with an empty set, right? And then you go over all the points of P, and if the distance of P to the current net is larger, strictly larger equal than R, then we add the point to the packing. Right? So, and that's it. Right? And we return it. We return the packing we compute. That's the algorithm. Naively, if we don't do anything smart, computing the distance this can take linear time. Computing the closest point in the packing to P takes linear time. And we have to go over all the points. So if the size of P is N, this running time is, of course, N squared, which is kind of disappointing. Okay, can we do better? So let's look on the case that the point set that we are trying to compute our packing for is in the dimensions, right? And in particular, I'm going to describe the algorithm in the plane to make it clear what I'm talking about. We have n points, right? And R is given to us as this is the given radius. And we want to compute a net for P, right? Okay, so we want to implement the above algorithm, but that's not going to quite work without some being a bit more clever. So if we want an efficient algorithm. So the first trick is we are going to build the grid G of R. To remind you, this is the grid where the side length for R, right? This is R, etc. And we throw the points of P into the grid, right? This means for each point, we compute its ID, we throw it into the hash table, etc., etc. Now for every grid cell that have points, we have an associated list of the points stored there. P1, I don't know, P17, etc., etc. Right? Okay. So now let's think about what we want to do. Well, we want to run the same algorithm as before, right? So, and to this end, what I'm going to do, I'm going to maintain for every point a distance, right? So there's going to be d of p, and d of p is going to be d of p is either going to be it's going to essentially have two values. Either you can in fact literally think about it as a flag, but it's going to have either the distance. It's going to roughly be, so maybe I should write it like that. It's going to be roughly the distance of P to the current net. Okay, now what I say, why do I put the equal in double quotes? It's because I really don't care about the exact distance. I care about whether the distance is bigger than R or smaller than R, right? This is the threshold of whether to pick it to the net or not. So initially, we set d of p of all the points to be, if you want, larger than R, or if you want conceptually, to be infinity, right? Initially, everything is large. Okay. Let's mark it as infinity. Being further away than R is infinity. And now we apply the same loop we did before, right? For P equal P for every point set, we're going to do the following. We compute the cell in the grid G of R containing P. Right, and the idea is that now we need to broadcast to all the points in this grid, in fact to all the points in the cluster. So let me compute this. Q would be all the points P cluster of the cell, right? So those are all the points around the cluster. So here is let me maybe zoom in. We have the current cell, and we compute all the points inside the enlarged region. That's the cluster, right? And we extract the list. Notice that the list might be long, right? This is so that's fine. We compute the cluster, and this still takes constant time because this is just going to return us a list of the points stored in every grid cell in the cluster. And now we have two options what we have to do. Well, right, or in fact I should maybe have written it in the top. If d of p is smaller than R, then continue. Right, this point is already covered. We cannot do anything with it. We care only about points that are not covered, right? So when we got here, we know that the point is not covered, so we're going to add it to the net. So let's do that. The net is going to be n plus p, right? I'm sometimes going to use this informal notation that really means n union with p, right? We add the points p to the set. And now we need to update the distances, right? So for every point Q in Q, right, we're going to set D of Q to be what? The minimum of dq, the whole distance, and the distance between P and Q. Right? And that's it. Here we are talking about Euclidean distance, so we can just write Euclidean distance. Okay? And that's it. That's the algorithm, right? We scan all the points. If the point is already covered, we move on to the next point. If it's not, we cover it, and we update all the points in its cluster that this point might be there, might be covering them, right? Not that all the points outside the cluster of the points, right? If the point P is here, any distance outside the cluster, this distance between P and points outside the cluster is strictly larger than R. So even if P can cover them, we don't care. It's too far, the update to the distance doesn't matter. So that's that. The correctness of the algorithm is obvious, right? We are maintaining this below R, above R information in the distance for each point, for the points we picked in the net. All the points we picked on the net are distance each from each other, and in particular, in the end of the run of this algorithm, we just return the net. Okay. Now, the interesting question is, so correctness hopefully is easy. Hopefully is easy. But the more interesting question is the running time. And the running time is kind of a fun game. So the basic idea is we're going to look on a grid cell, right? The grid cell has length R. We are now talking in the plane, the same argument will apply in higher dimension. So if it's a square, it's R by R. And whenever we pick a point from this cell, we essentially cover all the points in distance R, right? Strictly smaller than R if you want to be more precise. And then, of course, it might be that there is another point that is not covered that we discover later on and we add it to the net and so on. That's fine. But of course, since the points we add are at least in distance R from each other, and as we said earlier, a square can have at most 4 points in distance R or more from each other, it means that we can generate, this grid cell can have at most 4 times that we generate a point, add a point from it to the net, right? Okay, so look on a grid cell and think about the list of points that it has, right? This list might be very long, right? And when do we scan it? Well, we scan it whenever we pick a point to be in the net from this grid cell. But this can be at most 4 times, so that's not a problem. I'm allowed to scan the list 4 times. But the more important observation is that we might, of course, scan it because we picked a point outside the cell, right, from the cluster to be in the net. But if we do that, we also scan the list. But the key observation is that, there are at most 9 grid cells in the cluster. Each one of them can initiate can have at most 4 net points. So overall, or packing point. So overall, there are 36 packing points, which is off 1. So the list of this cell would be scanned 36 times. So every time we scan a point, you can think about it that it can happen at most 36 times. We have to pay only for the price of scanning the point. That really is the only quantity in this algorithm. It's not obvious how to bound. But since every point gets scanned at most 36 times, it follows that the overall running time of this algorithm is often. So the running time is often. Okay, so we get the following pretty amazing result. At least I think it's pretty amazing. So one can compute in our packing for a set of points, a set of n points in RD, in of n time. And again, this uses flow function and hashing and so on, but that's kind of very neat. And that's all I wanted to tell you about packing at this point.